Thanks. Do you hear me well? Okay. So before starting, I would like to thank the organizers for organizing this nice event and this very nice workshop, which I really appreciated. And also for inviting me to give this presentation on what we do in Paris at CIRT. So the topic of my talk will be short-range force sensing with a trapped atom interferometer. So I will not have to spend much time to motivate this work. I mean, we are interested in measuring short-range forces, and especially the force between a rubidium atom and a surface in a range of distance from very short to a few tens of micrometer, where a Casimir Polder interaction is at play, actually. And also, this experiment aims at performing tests of gravity at short range, provided that we are able to precisely measure this Casimir Polder force. So this force is actually very small. If you take a rubidium atom at a distance of 1 micrometer, it's a force as small as 10 to the minus 24 Newton. So, and at 10 micrometer, it's 10 to the minus 29. But I will show that we have enough sensitivity to measure such short forces, small forces. Important feature of these forces is that they have a very fast scaling with distance. So you need a probe that has a very good spatial resolution. And we also aim at reaching extremely sensitive measurements and also a good control of systematics. And this is a motivation for using cold atoms and using atom interferometry techniques to perform this measurement. The very principle of the measurement is just briefly illustrated here. We just have a superposition of two states that are actually at different distances from the surface. And we will these are the two paths, say, of an atom interferometer. And by recombining them, I will measure a phase which will be proportional to this difference in the potential energy between the two wave packets. And this difference in potential energy contains, in this geometry where this lattice beam in which the atoms are trapped is vertical, contains a difference in the gravitational potential energy, but a difference related to other forces, Casimir Polder, and eventually exotic or fifth force. So the principle is then to trap atom in a vertical lattice, and this is the Hamiltonian which is at play, where we have this kinetic energy and the periodic potential. So this is the Hamiltonian of an electron in a solid. So this leads to Bloch states and energy bands and delocalized eigenstates. But if you had a tilt, you break this translational invariance, and the eigenstates are no longer completely delocalized states. This is known from solid state physics because this is pretty much the problem of an electron in a crystal, but in the presence of an electric field, that the eigenstates of the system are the so-called Wannier-Stark states, which represent quasi-eigenstates of the system. These are actually resonances in the spectrum, but they are very long-lived, so we consider them as eigenstates given their lifetime, even at the shallow lattice depth at which we operate. These eigenfunctions are actually localized in the wells, centered onto the well. And an important feature is that the energy difference from one state to the other is simply given by the increment of the gravitational potential energy when you climb from one well to another. And this sets this energy scale, which gives this Bloch frequency, which is about 500 and so Hertz in our system. Interesting is that you can drive transition between those states using a laser. So here you have a ground state and an excited state that you connect with a laser. So these are electronic states, and each of these electronic states has this ladder of external states that correspond to the different Wannier-Stark states. So if you drive this, if you put the laser on resonance with the bare frequency, you drive a transition staying in the same well. But if you detune the laser, you can couple atoms in different electronic states, but also in different Wannier-Stark states. So you have some kind of laser-induced tunneling that you can tune by simply adjusting the frequency of the laser to match this change in the energy. What we do is a bit different. We do not use like a single photon transition. We use in our system rubidium-87, and we drive 2 photon transition between the 2 hyperfine states of the ground state. But with a Raman transition, we can basically do a 2 photon transition between different Wannier-Stark states. One simply has to replace the momentum of the light by the wave vector of the light by an effective wave vector, which is the difference between the wave vectors of a 2 counterpropagating laser, and this resonant frequency then here that we have for the bare transition corresponds to the hyperfine transition of rubidium. So since we can couple those states, we can do some kind of Ramsey interferometer by preparing using a pi/2 pulse coherent superposition of those 2 states which are in different wells. And then we just let it evolve and we recombine. And what we observe when we scan the frequency across this transition are these Ramsey fringes. And now the game is to measure the position of the central fringe, which tells about the bare frequency and number of times the Bloch frequency. Delta M is the change in well index. So delta M equal 1, I just change well index by 1. So quickly here, just present details on the experimental setup. So we do this in a 2-chamber experiment. The bottom chamber in which we prepare via evaporative cooling an ultra-cold sample of atom that we then transport by about 30 centimeters in this second chamber in which we have placed the surfaces of interest, which are actually dielectric mirrors. And once the atoms are there, we recapture them in the lattice. We state prepare, we do the interferometry, and then we detect the output state by fluorescence. So this system as such looks like a bit naked, but once you have all the lasers around and it becomes really messy, we have to actually align many lasers along the vertical direction. So in addition to this vertical laser that provides the lattice potential, we have a transverse confinement which is provided by an infrared progressive wave. We shine the Raman lasers from the bottom and then they get retro-reflected on a mirror which is here. And in addition, we also have 2 beams that we use to actually transport the atom from the bottom to the top chamber. So briefly, this transport, for this transport, we use two lattice beams, which are detuned by some hundreds of gigahertz from the D2 line. And we have a control of the relative frequency and amplitude of this lattice. And we use it to realize, to accelerate the atom using Bloch oscillations and transport the atom over this 30 centimeter distance. So this process is not super efficient. So this is the number of atoms we get at start as a function of the final temperature at the evaporation. We typically transport something like at max 25% of the atom. And then when we just recapture them into this mixed trap, the combination of the lattice potential plus the infrared for transverse confinement, we have an additional 30% efficiency. So in the end, we have a bit less than 10% atom transported. So then they are at the top chamber, and this is a closer look at what it looks like. So we have a support here, which contains, in which we have installed 2 different mirrors. These are 2 super polished substrates, one out of fused silica, the other one of PK7. They have a trichroic Bragg coating because they have to be highly reflective at 532 to realize the lattice potential, and they have to transmit the other wavelengths of interest here, which is 780 for the Raman and Bloch and for the transverse confinement. We have put them in a translation stage so that we can move them in and out. In addition, we have put some electrodes. So we have 4 linear electrodes here and 2 circular ones, and I will explain why later. And this red cross corresponds to 2 retro-reflected beams that we use for the fluorescence detection. So since with this transport, we have actually a good control of what the final position of the atom is, we can actually use it to determine the relative position of the atom with respect to the mirror. So the principle is simple. We transport the atom up to a smashing part of it onto the surface, and we detect the fraction that remains. And this provides not only a measurement of the relative position, but also of the size of the atomic sample that you extract from this fit of this Earth curve. And we see that we have typical vertical size, Gaussian size of a few micrometers that we can reduce by recompressing a little bit the atomic cloud at the end of the evaporation. And for the measurements I will present, we are more like with a 3 micrometer size cloud. Okay, so what is then the effect of having an attractive force in the interaction of the atom with the mirror? Very simply, this sketches the effect of an attractive force as a displacement of those Wannier-Stark states, which get displaced by this additional force, so that the frequency difference between two consecutive wells is no longer the Bloch frequency, but it gets shifted by the presence of an additional force. And this will become a large displacement when you are very close, and when you go far away, you get back this Bloch frequency. So this is what we see. I mean, this is a zoom on the center of the interferometer fringe pattern, where we have two different distances. One is where we are actually very far, 500 micrometers from the mirror. Another one where we are a bit closer, 40 micrometers. And here you clearly see a shift in the frequency that amounts here to about 2 Hertz. So you see that we have a pretty noisy signal, since we have a relatively small number of atoms. Also, the interrogation time is relatively limited, and this because contrast decreases when we bring the atom closer to the substrate. So here you have contrast decays as a function of the interferometer duration when we are far from the surface, a bit closer, and when we are very close to the surface at a few micrometers, so that we say operate with typical Ramsey interferometer times of 100 milliseconds or so. And this arises from like inhomogeneities in the light shift of the tramping potential, parasitic forces, which are arising from stray light, but also electric fields. And at very short distances, actually, even Casimir Polder force is a limit. So to evaluate a bit the performance of the sensor, we just do a stability analysis by calculating Allen standard deviation of the frequency measurements. What we actually do is our differential measurement, where we alternate transition by climbing by 6 wells, or climbing up or down by 6 and -6. And with that, we can separate actually changes in the clock frequency, which corresponds to the average between those two frequency shifts, and the Bloch frequency, which we get from half the difference between the two measurements. And this is the typical Allen standard deviation that we get with Bloch frequency stability of 0.28 Hertz at 1 second. So this averages down to, say, 5 millihertz or so after some thousands of second measurement time. This is a frequency resolution, relative frequency resolution of about 10 to the -5 on the measurement of the Bloch frequency. And in terms of force, this is the stability we get at 1 second measurement time, and it averages down to the 10 to the -29 Newton level. So now, this is what it looks like when we display, when we perform force measurements at different distances from the mirror. These are 3 data sets which have been taken over 3 months or so, with 1 month interval between each. So we clearly see a very well resolved 0.6 Hertz shift. So it's about 10 to the -3 change in the Bloch frequency. So it's equivalent to a milli-G acceleration, say. And this is measured with typically % uncertainty. And you see that it decreases the Bloch frequency. So this is a signature of an attractive force, since it opposes to the gravity acceleration that attracts the atoms to the ground. And if we zoom in the region of interest, we actually see that we have a large force, much larger than what is expected from a Casimir Polder contribution. Since we already have decent measurable force at distances where Casimir Polder is usually impossible to see. And when we are very close to the surface, the force we get is somewhat twice larger than what we expect. So what is the reason for that? I mean, this is somewhat expected and known, and this is related to the presence of adsorbed atoms on the surface. This was something that was already identified as a major systematic effect in the experiment by Cornell, and I just mentioned those two papers. So atoms adsorbed on the mirror, they behave like little dipoles, so they create electric fields, and parasitic electric fields that have large gradients, which leads to parasitic forces. So you can model, for instance, a distribution of atoms adsorbed on the surface with typical size of order of the size of the cloud that we bring to the surface or so. And you can, with such a distribution, you can try to reproduce the data. So by trying to fit the longer, well, whatever was above, say, 20 micrometer with this kind of distribution, we find a fairly good agreement with parameters which do not look like that reasonable because the number of atoms is very large, but for the size, it makes sense somehow. And interesting is that this, if we fit correctly the long tail, then when we get close, it doesn't work. But if we had the contribution to the Casimir Polder force, then we somewhat have a reasonable agreement with what we measure. So then how to cope with those effects? And this is the reason why we have those electrodes I mentioned. Adding an homogeneous electric field to the parasitic field, you change the force and you have a supplementary force, provided that your applied field is homogeneous, that is proportional to the applied field and to the electric field gradient. So this allows you to actually measure this gradient. This is what we do. It's simple. You just apply different voltages so that you change the electric field and you measure the change in the Bloch frequency as a function of the electric field applied at different distances. For each distance, you get a gradient, and then you can reconstruct, say, the evolution of the gradient of the electric field as a function of the distance. And with that, that's all I have to say on that. This is really work in progress. So we have to work on that to try to eliminate those systematic effects. And for the time that is left, I just want to discuss BBR stuff somehow. So can we use our system to detect blackbody radiation? So using like formulas that I took from this paper already mentioned many times, and considering that I'm able, for instance, to hit my mirror, which is a half-inch mirror, and like increasing the temperature by something like 100 degrees, I would end up with a force which is actually much smaller than one I can resolve, and which is in this range of distance I'm looking at, fairly constant, since I have to go out by a distance which is the size of the mirror to see that this force changes. If I would have this radiating surface much smaller, say 100 micrometer or 20 micrometer, then this would be something that would make a signal that I will be able to resolve, but these are not very like reasonable numbers in terms of mirror size. Note that this experiment is not meant for that, since we are interested in measuring at very short distances and taking and having the possibility to resolve a dependence on the distance. In the past, we did use this sensor and optimize its stability very far away from any surface without transport and so. And at that time, we had much more atoms and a much better contrast, and the stability was actually 2 orders of magnitude better. So in a dedicated experiment where I would bring this radiant object close, I would certainly be able to detect this effect. Another interesting thing is this temperature dependence of the Casimir Polder force. So I just put here this picture from the paper of Cornell, where they actually measured an increase by a factor of 3 of the Casimir Polder force at this distance of, say, 7 to 8 micrometer. So what we have in our case is a Casimir Polder force that leads to a shift in the Bloch frequency of about 0.1 Hertz at this very distance, which we can measure with an uncertainty of 5 millihertz, which is 5%. So you see that it's significantly better in terms of resolution than what was there in this paper. And this is certainly something we can do by heating the sample and doing this measurement with ideally a much better resolution. And with that, I will conclude by just highlighting a little bit what is next to be done. I mean, we definitely have to compare this E-field gradients maps with a model distribution of the adsorbed atoms and try to reconstruct pretty much like what Cornell did, this E-field distribution, so that we can correct the measurement from this parasitic force. This is, if we live with this bunch of adsorbed atoms on the surface, but there are also ways to, if not desorb, at least make them diffuse over the surface. And then if we are able to do that, then we can actually do a fair comparison between the measurement and what is expected from the calculation. And that's it. So I just want to mention the contribution of Luc Abzil and Yann Ballan. We are the two PhD students that have been working on that, with a postdoc, Xiaobing Deng, and many other people here that have contributed on this project that is already a long-standing project in our lab. Thank you.